Let's see. Hmm. I actually don't know whose next week's speaker is, so I have to look that up. Let's see. Totally forget. Is that right? It is, of course. Rob Scott. You here today, Rob? No. So Rob's going to be talking about deploying self-healing services with the old Kubes, the Kubi, Kubernetes. So come out for that. Should be fun. Let's see what else. We want to thank these lovely people here for making that food possible, as always. And your company is looking to sponsor a small organization, help grow the tech community here in Chattanooga. You know where to look. All right. I don't have much more to say. Anybody want to give a shout out to a meetup they're running or any kind of events coming up? All right. Next week is I'll do mine. Elixir meetup. We continue on our journey to finish programming Elixir, and then I don't know what we're gonna do after that. But if that sounds interesting to you, you should come and be a part of the conversation and help us decide. All right. Without further ado, we've got River here. River's going to give us a talk about how to simulate a universe. Everybody give it up for River. Come on. A little bit more. Yeah.
All right. Can everyone hear me? Yeah, I think so. All right. Sweet. Okay. I'm River, Kanies. I am a local full stack web developer, and I love to play with machine learning algorithms and simulations of all sorts and sizes. And a couple months back, I came across a fascinating book called A New Kind of Science by Stephen Wolfram. And it talks about something I'm sure we're all very familiar with, which is how to simulate a universe. But anyway, I thought it was fascinating and thought people would like to hear about it, so here we go. Okay, I wanted to start out with a disclaimer because this is like, it's pretty far out. It's just conjecture at this point. Some of the concepts are really physics and ML intensive, so feel free to stop me, ask questions. I may not be able to answer them, but I can try. And yeah, I'm going to talk as if I actually know what I'm talking about, but yeah, it's all theoretical. All right, so just a quick overview. How do you simulate a universe? So basically, the theory is you just have a very, very simple program, and there are actually a ton of different programs that'll work, and I'll explain why in theory. But basically, there's just a simple evolutionary program that will develop your universe step by step. So you start with some simple initial conditions, run this program on it again and again and again, and eventually your very small initial conditions will turn into a huge data set that is pretty much describing the state of your universe. And then to actually recognize that this big, complex data state is actually, something that we can recognize as being a physical universe, we do feature extraction to find things like particles or universal constants like the speed of light, and compare to what we think we know about physics now based on the observations that we've had. So, traditional physics. So if you follow these steps and you're able to reproduce physics as we know it, then I'd call that a universe. So that is what this talk is about. All right, so what's the deal with a simple program? Like, if you're going to simulate something as complicated as the entire universe, you might intuitively think like, oh, that's a really complicated process. And, maybe it is, but the assumption that I'm going to be making in this talk is that really the simplest program can generate all that complexity, the same way that evolution generated all the complexity of life, essentially. And as a long-time, physics hobbyist, and I got a degree in mechanical engineering, so I've spent a lot of time thinking about physics and the nature of our universe and so forth. And I've always been really attracted to the idea of, like many physicists, of a very simple, elegant equation or set of equations that can describe, any number of higher level processes. So that's just one of the intuitive reasons for even exploring this possibility. But then it turns out to be quite promising. So how can a simple program create all the complexity of the universe? And I pretty much talked about this already, and I'm about to go much more in detail on it. But basically the same way that the simple process of natural selection created all the complexities of life. So to kind of give some intuition into like how this is possible and what kind of programs I'm talking about, I'm going to be showing you some pictures of something called automata. And there's a distinction between cellular automata and mobile automata, which isn't all that important for the purposes of this talk. But basically what it is a very simple program. And as I've already said, you start with very simple initial conditions, then run this program step after step, and the automata evolves, and it's very discrete. I'm going to be showing you pictures that are binary. It's just a grid of squares that are either black or white. And you start with a row of white squares with one black square, and then you just run the program on each row, and it's going to generate a bunch of complexity. And so we'll see that it generates infinite variation and true randomness. So here's pretty much the simplest program that generates that behavior, the true randomness and the infinite variation. And so basically the program is if cell I, so basically we have this row of cells at the top, and they're all white except that one in the middle is black. And then to generate the next row, we're going to run this program on every cell in that first row. And what the program says is if the cell in question is, let's say, black is true and white is false. So if the cell in question is black and the cell to the right of it is also black, then the cell under the cell in question for the row that we're generating right now is going to be the value of the cell to the left. And then otherwise, it's going to be the opposite of that value. So it's a pretty simple program, and on the first run, it just generates 3 black squares, pretty much right under that first black square. Then on the second run, it starts to do some interesting things. We have 3 black squares, but they're spaced unevenly. And then as you go down about 10 more layers, it's not super interesting. But once you go down about 100 layers, you start to see triangles and some little lines forming. And then triangles are getting bigger, and there's like this vein going off to the side. And it's starting to look like it is truly random. So as we keep running this, it gets more and more random, and you see more and more interesting features. Like this vein right here, that's doing something pretty unusual. And then there's like, it's pretty chaotic filling up the rest of it. And as we zoom out even more, it gets more and more random. Does anyone have any thoughts or questions that they'd like to bring up at this point? Okay. Right, okay. So the question was, why am I saying that it's random? And he pointed out that it seems to be very periodical, and there's a lot of repeating geometrical features and so forth. It seems like, you know, maybe there is kind of some order to, you know, how all the similarities in all these stripes or strata, if you will, and then maybe somewhere in there. And I agree. I mean, that's a good point. It doesn't look completely random, and there are definitely some repeating shapes like the triangles and some of this here. But the reason that it's random is that there's no shortcut to finding out what the value of any particular cell is. You have to run the entire simulation to find out what the value of any particular cell is. Yeah? Right. Right. Okay. It was pointed out that maybe it's not truly random, but it's certainly complex. And yeah, okay, maybe it's not truly random. That's not really something that is crucial to the argument that I'm making, but yes, it is complex. It goes from something very simple to something very complex. It's certainly predictable, but it produces seemingly random behavior. That's really all there is. Anything else? So then it starts to get really interesting when you go even further. You get some really odd looking kind of features popping out. And I think that somewhere in the book I think he actually talks about this representing a particle maybe. But really just more examples of the very unpredictable behavior that ends up showing up from such a simple program. And so here's some other programs running, and you can probably barely even see them, but you get all kinds of interesting shapes. Another one. No, it's a different algorithm, just a slightly different algorithm, but pretty similar, pretty simple, and you can get all this same behavior. Okay, so I'm saying that complexity equals universe. Yeah, that's pretty much the argument, and the two main theoretical leaps that you need to make to really understand how this could make sense are the concepts of universality and computational equivalence. So I'm just going to read these definitions real quick because, and I can't scroll down on this. What? Okay. All right. Okay, so universality. The idea is that any program with fundamentally complex or random behavior can and will inevitably generate any and all others at some point in time. So that's really profound to me. I mean, when I first read that, I was just like, wait, just scratching my head for a second, thinking about it. And then I realized how elegant that is, if that's true, and how much sense it really makes that any of these simple programs could be the fundamental process that really governs the entire universe, because it's saying that it can actually generate the behavior that emulates any other one of these programs. And I'm going to give some examples, like pictures of this actually happening. And then the other important idea is the idea of computational equivalence, which I can't read the definition right now because for some reason this won't scroll. I guess I could. Okay, there we go. Okay, so the idea there is any program with fundamentally complex or random behavior is equivalently performant in terms of complexity over time. So the idea there is that it shouldn't really matter all that much which one of these programs you choose to use, because fundamentally, like at the binary level, the complexity that they'll generate over time, or computing time, or however you're going to measure it, is equivalent, essentially. So, any comments on that? Universality, that's pretty cool, right? Yeah, I thought it was pretty cool. Okay. So here are some examples of like showing universality. So on the left, there's just, it's really the simplest algorithm ever. It's not even generating truly random or complex behavior. It's completely predictable. It's just a black triangle. The program is if the cell above or to the right or to the left in the previous row is black, then this cell is also black. So this would not count as a program that you could call that has the property of universality, or that you could use to generate a simulation of the universe. But this other very, very interesting program on the right is emulating this much simpler program, just based on the initial conditions that were fed to it. And you can see there's like 3 orders of magnitude more cells in this, and they have varying shades and so forth. But nonetheless, you can see that you can break down any chunk of these cells and treat it as being either a white or a black, and it translates over quite nicely. So then this same program, the same one on the right, is also shown emulating this fractal pattern, which fractal are also not quite random. They're predictable. Well, random, as I've been saying. They're not truly complex. They don't generate truly complex behavior. But again, this slightly more complicated program is shown emulating this program. And then finally, the same program, given a slightly different set of initial conditions, is emulating the first program that I showed you, which does have the property of generating true randomness. So this program on the right here is capable of emulating this program and any other program, actually, is the theory, at least. Okay, so I'm about to transition into a different section of the topic. If anyone has any questions about that section, that would be good. You can find it if you look in the book, I believe, but I didn't write it down. I'm actually not 100% sure that he tells us what it is, but I'm pretty sure it's in the book. The book's free online. It's called A New Kind of Science by Stephen Wolfram. Okay, so how do we go about actually choosing a program and actually simulating the universe and showing that this isn't just a hallucination, that this is like really something we can do, and it really does generate the physical properties that we would require to observe in such a system to say that it is in fact a small universe. So, as I've been describing, the theory is that any program could work, or any of this set of truly complex programs. And so then the real question is, how do we design the framework, which is like the grid, right? I've just been talking about grids so far, but it's actually much more useful to use a three-dimensional network, as I'll describe in a minute. So determining what kind of grid layout you want and which particular program you want to use, as well as which particular initial conditions you choose to start with. Making those decisions are all about designing for feature extraction. So that's where the machine learning aspect of this talk comes in. To actually say, you know, this is a universe, we need to demonstrate that there are particles that follow the physical laws that we know and love, such as Einstein's relativity. We need to be able to recognize that the speed of light is a constant within here, or at least looks to be at a high level. We need to be able to, you know, recognize physical forces and such. So it turns out that it actually works really well if you use a three-dimensional network as opposed to a grid. And it may seem like this is fundamentally different, but you can represent the data in any data you could represent in a grid, you can represent in a three-dimensional network. And it's much closer to, like, the whole intuition that we have about space is much more closely translatable between a three-dimensional network and the space we know and love than to try to look at a 2D image and recognize the 3D, you know, universe that it's describing. So it makes a lot of sense to choose to use a 3D network to run as the framework to run our program in. Yeah, so space corresponds quite intuitively. And here's a picture of, you know, how you might actually lay out that three-dimensional network on the far right there. So one very interesting point to make is any network can be represented by a network of nodes with 3 connections. And the proof is right here in the bottom right corner. If you want a network that has 4 connections to one node, that becomes 4 nodes, each with 3 connections, and you get the same ability to transfer data and the same connections there. And then if you have 5, it's really the same. You can always break it down into a set of nodes that have 3 connections. So in the grid itself, it might seem like this is, you know, making things bigger when in physics things should be a certain size. But the 3D mapping isn't one-to-one. Like the 3D grid here, all of those lengths are completely arbitrary, and the only real relevance that adjacency has in this grid, or spatial adjacency has in this grid, is really just the connections that it has. So a particle might look like some weird bamboozled spider-looking thing and move in really odd-looking ways. But still, the adjacency of different particles in this system allows 2 adjacent particles to have physical interactions and so forth in a similar way. And then time, in this whole theory, you can just forget about the idea of space-time. It doesn't really help you think about it because we're running this, we're assuming that the universe is a discrete simulation, basically, although it's not a simulation, depending on how you look at it. But yeah, time is just time as you would think, and space is, in this 3D network, it's pretty close to space as you would think of it. And then that's just a picture of the universe growing over time as it goes from left to right. Doesn't really show much more than that. Okay, so any questions about the 3D network? Does that make sense why we would approach this and why it's valid to do that? All right, so then just something worth, some things worth touching on here. In any kind of feature extraction, it's really important to be able to summarize your information, and that's really what feature extraction is. It's a process of taking some complex, not all that recognizable thing and convoluting it to get a summary that looks like something we do know and we can compare it to. And then, so one method that should be pretty familiar to anyone is compression. So for example, with that first program I was showing you that had all the triangles, you could use any number of compression methods to reduce the information in all those triangles to be a couple bits instead of however big the triangle was. And then as I was just mentioning, convolutional neural nets are great for taking complex, vague sets of data and finding, what similarities are there between this chunk of state and this chunk of state, or, the universe that we're trying to simulate and the high-level observations that we expect to see based on traditional physics. And so that's really where you start to bridge the gap is you approach it from both sides. You take what we think we know about physics and makes a simulation that represents what we would expect the simulation to generate if it's going to have particles and so forth. And then we run our simulation and we do feature extraction on both simulations to find where the connections are. So you can get very similar features from very different seeming sets of data using these machine learning techniques. So if you do a great job with feature extraction and you're able to recognize the natural laws that we would expect to see in a universe, and it really does resemble the physics that we observe, then I would argue that that's a baby universe. And the conclusion here is Wolfram was able to, or claims to have been able to actually reproduce Einstein's relativity and the speed of light and so forth, actually claimed to see particles in the simulations that he's done. And yeah, I think that that's absolutely fascinating. And I think that this whole vein of science, of looking at it from like a ground up perspective, really lets us dive into deeper than anything we could observe. Like it just starts with a guess, but if we can produce the physics that we do observe, then we know, or I like to think that we know that we're actually looking deeper into the true nature of the physical universe. So yeah, that's my talk. There's my business card. I am a local local full stack web developer, and I'm doing independent consulting right now. I write a lot of JavaScript, Ruby on Rails. I do some Elixir as well. Yeah, if anyone is looking for a developer, please feel free to reach out to me. Always love to meet new people, especially if they want to pay me money. So yeah, any more questions? Should we give him a mic? I don't know if I can answer this question, but it sounds like an interesting discussion.
Sorry, I was just noting that with the reproduction of that code, that it's more of a crystallography type structure as opposed to biological. I mean, there's no randomness or input genetic variation. It's more of an equation as opposed to like a regression model that you'd use in machine learning. So I mean, is there some error component that is later part of the model that's able to create this, or?
I think that you're wrong, probably.
Oh, that's fine. I just want to understand. It won't be the first time.
I'm not entirely sure what you're asking. You were saying that it seems like there can't be like organic kind of complexity.
Well, with the regular repeating structures, I'm having trouble seeing how it go from crystallography as opposed to actually biological life. That's what I was curious about.
I don't know that that question has been answered in science yet, right? Like, how did we go from particles to life?
Okay.
It's a hard question, but I believe it happened. So I think that if this simulation can generate particles, then it can generate life.
Okay. Well, then the interesting thing is I know the Hadron Collider results recently gave hint of other particles that we don't know about yet. So it'd be interesting if Wolfram's work would actually show those to exist before.
Right, exactly. And that's what's so interesting about this idea is if we can show that it does represent the observable physics, then we can see, what else is in this simulation that we haven't seen yet. And what does that tell us? And that's really the value of looking into all this.
This kind of like interestingly ties into that. I guess I was going to ask, these things do seem like, in a certain way, somewhat predictable, right? But really complex. And I guess like part of the question I was going to ask was, what scale so if like a large function of evolution is time, then like what scale of time are we looking at before we start seeing things that are complex enough to be considered a universe? And also, how does that affect, these things looking more like crystalline structures or whatever? Like on an atomic level, atoms are as well. They're very predictable. Like we know, yeah. So, but when it's, something extrapolated over a massive amount of time or a large scale, then it kind of changes. I guess is there talk in the book on work of doing this on like, high performance cluster systems, or is it to that scale before they're starting to see that, or is it like running it on your laptop?
So I have no idea what scale you start to see particles. I know that he's very early in his research on this topic and that he has wild ambitions for, how to go further with it. And I mean, maybe he's made some significant advancements since I was looking into this, which was like about 6 months ago. For the other question that you asked about whether or not this is a universe, I would claim that it is because it has the potential of growing into the universe. So I mean, that's pretty much just an arbitrary boundary for me. In my mind, it's like, yes, maybe this is like 1/bajillionth of a second old universe, but it still has the potential of growing into that, which is fascinating.
What were some of the the more like the initial conditions that he puts into like his larger simulations and the equations, like is there self-referential behavior there where he's like, oh, I'm trying to expect a universe, so I'm going to put in some laws which end up generating the laws that, you know what I mean? Like, does he start just making decisions based on what he already knows about the universe? Or like, what are some of the the algorithms he's putting in the initial conditions, and how does he choose those?
Yeah, so, I mean, that's a great line of questioning, and I mean, I don't really have a great answer, but one of the fundamental arguments that he makes is that any set of conditions can be generated with any one of these programs if run long enough, and then depending on which one you're using, you can always just take a subset of the current state and treat that as the beginning of your new universe. You could think of it as like a slice of universe, and maybe this is really representing like an infinite multiverse or something. I have no idea. But any particular slice of it could be representing a single universe or any other intuitive concept, really, frankly. So, did that kind of answer your question? Cool. A New Kind of Science by Stephen Wolfram, I think.
All right, thank you all for coming, and come out next week for that Kubernetes talk. See you guys then.